Our next presentation comes from Serge Sharoff, University of Leeds, talking about large language models.
Okay, hello, and where is the slide? I hope that it will be there. Right, okay, so then I can, yes, okay, good, thank you. So I can start. Actually, I would like to continue the theme. One of the themes discussed in the panel is about users and software, and actually I'm a user. And I worked on language modeling for the entirety of my career. And then the change came in December 2022, when everyone realized that language modeling is cool, and I became Mr. ChatGPT at the University of Leeds. Right? Okay, but then in reality, the story of language modeling is much longer. Actually, the very first computer, it was designed, actually not very far from here, about 40 miles from here in Bletchley Park, specifically for the purpose of running a language model. So in that case, it was the language model. If you have different setup for encoding messages, then checking which of them leads to a reasonable text in German. It was essentially the way the very first computer was designed. And so then I'm not going to talk about that part. I will be talking about the project. So then I will be talking about several projects, but one of them was a project which was funded by UKRI right after COVID started. And the idea was to investigate the flow of information about COVID. So, and in the ideal world, you have solid research which translates into government policy, and then this is disseminated via mass media, and then this is discussed in social media, right? So then, reality is messy. And what you have is you have some references to research, and then this can be traced back. So then what we did, we mined PubMed, and out of PubMed, so we found some of the papers relevant to COVID, and they talk about 40 to 90% instantaneous penetration levels against viruses, and then with some decision that fabric materials provide only marginal protection, right? And then you have two governments talking about this, the same issue, and then at that time they were talking about this in two different ways, right? So what a large language model can do for you is, so a good language model will actually iron out the differences in the meanings expressed across those different sources, so that you can say that all three of them, they talk about face masks, and the first one and the third one, they talk about no need for having face masks, and then the second one is about the support for wearing face masks, and then you can also talk about functions, so then you have text from academics and also advice coming from the government. Actually, you don't need language models in order to get this stuff, because essentially a good traditional meta-analysis will produce roughly similar results. But what was interesting is the second part about mass media and social media. So what we did, we started collecting data from the newspapers and from social media, and the communications department of the NHS, they were partners in this project, and they were interested in the dissemination. So what are the discussions going on, first of all, about which topics, and one of them was about face masks, and to what extent there was support, and then what we found out was there, at least at that stage, there was overwhelming support for wearing face masks. And that was the first year of the project, it was 2020. In 2021, the NHS asked us to focus on a different aspect, and namely on vaccination. And because the vaccination campaign started, and they actually want, so then we all know that there was some resistance to vaccination, and what was interesting is to understand under which conditions people share things which, from the viewpoint of the NHS, they can be treated as misinformation, right? So one thing it's important to distinguish between disinformation and misinformation, right? So disinformation is an attempt to deliberately spread information which the author knows that it is false. What we quite often don't know whether the author thinks that this information is false or not, because in the first example, so it is just bollocks. So quantum connection, pulsating microwave frequencies, mobile masks, graphene oxide in the fatty tissues of all vaccinated people. But then there are people who share this information online. And what was important is to understand the conditions. So first of all, you have some texts which resemble academic research papers. They're obviously not academic research papers, but then when people share them and people like them, then they assume that these are real pieces of research, right? Then you have personal experiences, and again, you don't know whether it's quite possible that a person indeed had a negative reaction from a negative side effect from getting the COVID vaccine. But the point is that if there is then if some people are ready to share information of this kind, this indicates some discontent in society. And for the NHS, it was interesting to have some kind of tools essentially to be able to collect intelligence on certain topics, right? And again, a good language model provides you some of the categories, right? Whether this is misinformation or not, and whether this resembles academic texts or personal reporting, etc. Right. Okay. Yet another thing is that about 1/3. So then, when we crawl data, then about 1/3 of data came in the form of pictures. So language models, they mostly work with text, and this was 2021, before the widespread use of multimodal language models which can integrate seamlessly images and text. So in our case, essentially what we did, we developed a classifier. So in some cases we have just images, in some other cases we have images, they present themselves as images, but in reality these are texts, and we can do optical character recognition in order to extract the text and then work with them. And then finally, the most interesting case, and the case which we could not deal successfully, is the case of memes, in which there is a picture and there is a kind of illustration which shows something, right? And for this you need multimodal language models, right? And then essentially what we got in the end, we got some amount of data which we were able to collect. And we started with Twitter, which we followed with Facebook, and there was a problem. Essentially, so then when we started collecting data from social media specifically with the aim of getting more misinformation, then we found out that we were chasing the remnants of what Twitter and Facebook were not able to catch as misinformation, right? So then we listened to channels which were provided to us by the NHS, which were likely to spread misinformation, and then most of the time, by the time we started collecting data, then the post was already taken down by Twitter or by Facebook. So fortunately for us, we found out Telegram, and Telegram had a very lenient approach to collecting, to actually restricting any kind of information there, and it became also the leading channel for disseminating misinformation. And so you can see that the success rate in getting misinformation messages, so the numbers are in the number of messages we obtained from each platform. So definitely there was much richer troll from Telegram, right? And then with large language models, we made some predictions. So first of all, about the distribution of texts which pretended to be academic research or argumentative texts, etc. Then various topics. Again, so the most common topics in this corpus, because we focused on vaccines, but then there were also other topics present there at the same time, and also the other thing which was of interest to the NHS was also the age of people, right? And we found, so then essentially with respect to age, we essentially contradicted the assumptions of the NHS about younger people more involved in spreading misinformation, because according to people in the communications department of the NHS, so then all the people mostly read newspapers and watched the TV, and therefore they were less likely to be affected by misinformation. And we found that it was just the other way around. The older you are, the more likely you are to share misinformation. Still, this actually applied to a very small section of society, at least out of all data we collected. But there was this rise with age. So elderly people, they are less, so then they trust essentially more things on the web, right? So that was, right, okay, then the last bit about that project is that essentially we also apply some kind of linguistic analysis. So you have, as you saw, we collected some texts which are not misinformation and some which are misinformation, and we can apply some of the we can detect some of the interesting features. And one feature is the use of indefinite pronouns. So these are pronouns referring to something quite abstract, such as everything is a typical example here, right? And the other is about passives with the explicit use of by. This is used to actually demote agency, right? So then if we have this last example, human, so then I am a human not owned by big pharma. So then essentially, this is a normal sentence. But if you turn it backwards, so then big pharma doesn't own me, right? Then this already sounds strange in the sense that when big pharma doesn't have the same agency, right? As I. So I can say that I own a house. The house is owned by me, and they are roughly equivalent, right? So and then again, so then we can see the differences in the linguistic patterns, and then we can assume what is the reason for such difficulty, so the lack of precision actually in misinformation, right? And this is all great, but then the question is about what, so then as a user, so then how do I work on this? And the answer is by using HPC, right? So then this is the reason I'm here. And this is, again, so then I started working on language modeling when it was my PhD topic, and my PhD topic became fairly obsolete after the arrival of ChatGPT, but 25 years ago it was actually cool to work on it, right? So then you have, this was, so the language model is about the general language of questions, right? So you have questions, and in questions you have something like, so what is the salary of, or what is the price of? From the viewpoint of language model, they are very similar, and they also translate. So then in this case, if you treat this as queries to a search, to a database engine, then they translate into very similar SQL queries, right? But what is more, also you have variation. And the variation here is in the form of, for example, you can say, what is the price of something, or how much does it cost? So the syntactic trees in this case will be different, but the outcome in terms of the SQL query needs to be the same, right? And then it was fun to work on this, but then how I was doing this, it was by means of a language. Some of the people in this room can recognize it. That was Lisp. In Lisp, you can define macros, and then these macros can act as rules, and then you have a system for balancing the priority of the rules, in which case which rule fires. And then this is quite intellectually demanding. You can definitely for a task of designing rules for general questions in English, you could get a PhD at the time. So things became easier in the 2000s, and when I switched to using a mixture of Perl and R. So Perl is good for processing text, for extracting some of the features which were interesting for me from the text. The price for this is lots of dollar signs, percentage signs, at signs, etc. So then this makes it actually fairly unreadable. And then you feed this into R, which has much better statistical libraries for any kind of statistical processes. But then at the same time, this language is completely rubbish in terms of string manipulation. So I have an example here. Anything. So then if you want to do string concatenation, then it looks very strange in R, right? Okay. So that was how it looked like 15 years ago, and then something like a few years ago I switched I switched into using Python probably about 10 years ago. But then this is the kind of tasks I give to my students in linguistics, in which what they do effectively, they write 2 lines of code. So then they import the right library, which is at the top here, and then they load a language model which I created for detecting genres, and then it will output. So then what I have here again. So then remember I talked. So if you have this stream of texts, then you can classify them into argumentative or news reporting or fiction, etc. Right, and then essentially in 2 lines you import the right libraries and the right language model, and after that just all the inference is done essentially in 1 line. Right, training this language model used to be quite challenging. Still, so then I'm talking about 5-6 years ago, right? With the arrival of ChatGPT, so then in this case this is Google Colab, you can just write this up. So create a framework using the Hugging Face Transformers library to read a CSV file, etc., and then it outputs something which is actually right. So that you can just run this code, you can deploy it, and then after that you can train your own language model on this basis, right? So then this essentially, a kind of a question: where does this leave us in terms of our future? So on the one hand, it's much easier to do things, right? Then on the other hand, do we need this power, right? So why do we need students in linguistics running language models, and then probably they need to run existing language models, but then creating language models. So what is the rationale for this democratization? And then my answer is that they know something which people in computer science don't, right? So this is yet another example. So then this time this is machine translation. The machine translation task tries rendering the source text in this case from Russian, and it just outputs something which is not readable, or which is quite difficult to understand. Then you can look at the reference translation. The reference translation is quite clear, but then you see that the model failed, right? So the machine translation model failed, and now you need to fire another language model which can detect what actually went wrong. And that was a PhD from my students. So essentially, there is a whole class of some relations. So then one of them is a positive. And so in this specific case, this is a positive relation. So then when you have the title and then the description of someone having this title, this is a relatively rare construction. And if you have a rare construction, then it is quite likely that a machine translation model will fail this construction, but you need to identify what this construction is. In exactly the same way, if you again, so then we talked about bipassives, and you have and you can estimate the frequency of bipassives. So then this is the case when you have the agent demoted, right? And then you have some frequency in legal text. So then this was approved by somebody, right? So then the frequency of bipassives is higher. That's clear, because what legal texts quite often want to do, they want to demote the agency at the by foregrounding the actual act. So then what was allowed, right? And then they also mentioned by whom this was allowed. The thing is that if you take a large language model, Then in this case, and the frequency is like this. So then the frequency was about 100 per sentence. So then in sort of general English, then you switch into something like 50%. So okay, no, 1 per 50 sentences in legal language, but then if you ask a large language model, so in my case it was Llama, to generate a legal text, then it suddenly spits out it with the frequency of 1 bypassive per 28 sentences, right? And this clearly creates a kind of discrepancy between what is what is the expectation, even in the case of the legal language, and in the case of what you can get out of large language models. And you do for all these tasks, you do need a linguist to understand that this is the case of an appositive relation. This is the case of bypassives, and therefore empowering the users with the possibility of actually firing and fine-tuning their own language models is important. So I think that that's it. So what I wanted to say, essentially, large language models are good. And primarily for the task, at least the way I use them, is for the task of classifying texts into various categories so that you can predict many interesting things in spite of the inherent variation which is present in linguistic data, right? And then you can apply them to various tasks. And so this is another thing which actually came after the start of ChatGPT era and large language models, is that I started working on projects in fashion and in oncology, in psychiatry, and the latest project we have is its own democratization on improving democracy in the European Union. So then, okay, and then by means of using large language models, right? But then the interesting results we can achieve is if we actually know, if we collaborate with linguists, right? And they can actually train their own language models, and they can apply them in various ways, right? Okay, I think that's it, and there is time for questions.
Thank you, Serge. Do we have any questions?
Nice talk. What are the bottlenecks in scaling up simulations or theoretical modeling for LLMs? Is it just time to get used to the system, or is it which kind of HPC resources or computing resources are best suited for LLM work?
You do need GPUs, and in this respect, large language models are fairly hungry in terms of resources. And there is a limit, essentially, so that at least, for example, at least, we have clusters, and at the moment, there are 2 clusters at Leeds, and then there is also the N8 cluster at Durham, which I use, and they are quite often busy, and therefore, so if you have a 7 billion parameter model, then it can run on a single GPU. If you have a 14 billion parameter model, then it needs 2 GPUs. And then if you have a 70 billion parameter model, it requires 4 GPUs. And then getting 4 GPUs, for example, either at Leeds or at N8 at Durham is completely impossible. Right? So then you will with each and single run, you will wait for a day or so in the queue. Right? And because of this, most of the experiments actually done by me and my students are with sort of medium-sized language models, so then around the size of 7 billion parameters, which is far less than what ChatGPT offers. But at the same time, it would be nice to have more computing power. At the same time, if you focus on a specific task, so ChatGPT is better in doing everything, but in detecting genres, my own fine-tuned language model is much better, right? It is already better in spite of the fact that it is on the top of a 3 billion or 7 billion parameter model. So this is but still there is a bottleneck here. The other bottleneck is in terms of interaction and interface between hardware and HPC available and the skills of the students. So I mentioned the great potential for democratization from the use of large language models. But what is actually missing in this case is that, so then if you get output like this, so then at the bottom you have the learning rate and then the number of epochs. These are some of the things which are easy to explain to language students. The problem is that if you deploy this model on your ARC system, then sometimes it behaves in the way, so on your HPC system, it's just called ARC at least, right? On your HPC system, then you get sometimes you get good performance, sometimes you don't. And you don't know as the user where the problem is. And then even when you talk to software engineers, because they don't know precisely the pipeline you use, they also don't know where the bottleneck is. So that's why it expected to utilize the entire GPU and it utilizes only half of it. And then where the problem in the transformers library in terms of how I use the library or how Google told me how to use the transformers library.
Any other questions?
Yep. Okay. You'll be next.
I mean, large language models look convincing, and in a sort of conversational fashion they may appear to be, but they tend to make lots of mistakes, all kinds of ones. And there's an interesting paper you're probably aware of by some colleagues at the Oxford Internet Institute, which is entitled, "Do Large Language Models Have a Legal Duty to Tell the Truth?" Now, if you are driving, you must be careful not to drink too much alcohol. It's dangerous to bet, and so on and so forth. They advocate that we must cease careless speech, by which they mean polluting the internet, particularly with large language models that are generated maybe off credible sources and end up producing stuff that's actually degenerated and no longer fit for purpose, but which could in future be used for further training. And in the end, we get a consequence which is called model collapse that was published several months ago in Nature, where if you keep using AI data, your models degenerate into something which is utter rubbish. Could you comment on those aspects of your work?
This is definitely the case, and actually the machine translation community hit upon this problem much earlier on, because Google Translate is with us for the past 20 years, and it kept producing more and more texts, which was injected into the next generation of machine translation, and this usually led to the collapse in machine translation quality. And therefore, the task was actually to detect. So then when you do this crawling, then the task was to detect. So I don't believe in the power of regulation here. That so then preventing users from publishing more materials online is nearly impossible. What you can do, so then on the side of machine learning development, is to detect cases of automatically generated speech, and then reduce its impact on what is injected into your models. And I think that again, from what I saw, this is an efficient way of dealing with this. And the other question about hallucinations, yes, of course. Then this is the reason why. So then it's inherent in language models. It's the reason why they are powerful, because if you reduce the amount of hallucination in those models, they will not be able to answer some of the questions which were not in their original data, right? But then again, the answer for this is to develop methods for detecting hallucinations, and we are reasonably successful in doing this. So then, we are recently successful with the current generation of language models. New language models will come with their own problems with hallucination, and then we will have to fight them as well. Okay, thank you. Yeah, Mike.
So you partly answered what I was going to ask, which is related to that. You said that it takes a linguist to spot when machine translation's gone wrong.
Right.
Can you automate? You can automate that. Is that what are you optimistic we can do that?
Partly yes, but then still, in terms of analysis, then I would argue for the importance of linguists in large language models because they know language better. And then, in a sense, so then in this particular case, many things can be automated because what you can do, you can detect. So then, and this is actually what the student was doing. He was detecting appositive relations and then clausal complements, etc., automatically, and then seeing the difference in the frequencies between the well-translated examples and less well-translated examples, and then in this way, in this automated way, he managed to improve the quality of machine translation. But then it takes a linguist to actually to talk about appositive. So you need to know the right term. You need to understand that these are the reasons why something happens in exactly the same way, and this is coming from this different project. So then if you have bipassives, again, so then you need to know about bipassives, and because of this, the use of linguists is crucial in understanding where machine translation models go wrong, and possibly also improving their output.
Yes. Thank you.